Good morning, everybody. My name is Gabriel Laboy. I am a research specialist at the Global Computer Lab under Dr. Michaela Taufer and a recent master's graduate in computer science from the University of Tennessee, Knoxville. Today, I have the pleasure of presenting to you advancing the GEOtiled framework through scalable terrain parameter commutation. And to get started, I'd first like to discuss what terrain parameters are. Put simply, those are the physical topological features of the Earth's surface, such as elevation, slope, and aspect. And these sort of terrain parameters used in various earth science studies, such as predictive upscaling for soil moisture, determining fire propagation zones, and for mapping hydrological areas of interest. These terrain parameters are computed from what are known as digital elevation models, exactly what they sound like, digital representations of the elevation of the Earth's surface. And we have an issue here where these input files used to compute these terrain parameters have exploding file sizes as the resolution and region of interest increases. An example on the right is we go from Tennessee at 30-meter resolution to CONUS at 10-meter resolution. We see a 2 to 380 gigabyte increase. As for the open source libraries that can compute these terrain parameters, we have two of note here, which are the Geospatial Data Abstraction Library, or GEODAL, and the System for Automated Geoscientific Analyses, or SAGA. GEODAL is relatively fast, but does not offer any sort of feature for scalable multiprocessing, and Saga is far slower than GEODAL and also does not offer this sort of feature for multiprocessing, but does compute far more terrain parameters than the GEODAL library. So the solution for our work is we wish to update GEOtiled, a workflow designed by the Global Computing Lab, which integrates the GEODAL and Saga libraries to provide rapid, scalable computation of terrain parameters using methods of data decomposition and parallel computation. Specifically, our optimizations parallelize the cropping procedure, update the mosaic algorithm, and unify some multiprocessing processes to minimize overheads. So on the right here, kind of an overview of the GEOtiled framework. It's divided into 5 major steps. The first two sort of data preprocessing, which is where we first have to download the digital elevation models, which we gather from the United States Geological Survey. We merge the collection of files together into a single image, and then we reproject it into a computable format. In these next 3 steps, kind of what makes GEOtiled unique is it first crops the preprocessed data into a series of tiles with buffer regions, which is just copied pixels from neighboring tiles added to each tile. To preserve accuracy during computation, since terrain parameter algorithms do rely on neighboring pixel values to determine the value of a specific pixel, followed by the parallel computation of these terrain parameters for each tile, and then merging these computed terrain parameter tiles back together into a single image. In the new and improved GEOtiled 2.0, our work, we now have the addition of Saga on top of what we originally only had GEODAL. And with Saga, we compute 5 times more terrain parameters than with GEODAL. And also with our optimizations, we were able to decrease some of the computational costs incurred by Saga, since it is a little bit more expensive than the GEODAL counterpart. As for our optimizations, we first introduced concurrent cropping. So in the original cropping method, it had a window with corner corners that it slid across the original image, of course, specified by tile size. And this as the window was slid across the image, you would crop each of these tiles sequentially. So what we can do instead is first compute all the windows or corner coordinates we need, which can be done very rapidly. And then for all these windows, we can do the cropping process in parallel for a significant performance improvement. The second optimization is the updated mosaic procedure. So in the original mosaic method, it would take the overlapping regions, or the buffer regions from these tiles, and then average them together. We found that this process caused big slowdowns when we have more tiles to merge together. So for our new method, we instead crop off these buffer regions first, and then we simply concatenate the tiles together. And because we already have an optimization for concurrent cropping, we can apply the same concurrent cropping here to the cropping of buffer regions for performance improvement. Finally, in our third optimization, we have unified parallel processing. So right now with our previous 2 optimizations, we have 3 different instances of concurrent computation. And something to note here is that for any given elevation tile, it'll create a subsequent crop DEM, a subsequent computed terrain parameters, and then subsequent unbuffered parameters. So because of this sort of data pipeline, we can instead unify all 3 of these different functions into a single multiprocessing instance where all 3 of the functions are handled at once and still produce the same output. And this minimizes our overheads from spawning multiple multiprocessing tools. As for the result of our optimizations, given here in this graph, so this is a test case for Tennessee at 30-meter computed slope. And on our x-axis, we have decrementing tile sizes, where the smaller our tile size, the more tiles we produce, and the more concurrency we leverage. So as you can note, first, in our optimized behaviors, first we have now a constantly decaying execution time. And second, for our smallest title case, where we have 32 concurrent processes, we see about a 7 times improvement in our optimized case versus the unoptimized version. So finally, for our future work, we would like to, of course, continue to integrate more terrain parameters functions from Saga, as Saga is a rather large library, and the more terrain parameters we integrate, the greater the applicability GEOtiled can have to the earth sciences. And second, we wish to optimize memory usage. Both GEOtiled and Saga rely heavily on file I/O for reading and writing to new files, and so we would like to investigate new methods to try and minimize that to improve memory usage of the workflow. So thank you so much for listening. If you're interested in the GEOtiled software, here's a QR code at the bottom right you can scan. And of course, thank you to the team at the GC Lab for helping me out with this work, our collaborators at the University of Delaware, and the National Science Foundation for funding this work.